This presentation is a follow-up to Session 1 of Designing 3D Science Lessons for Hawaii-Focused Phenomena. I'm Lori Anderson. Some phenomena can be used to anchor a long sequence of instruction because they are likely to take many class periods to explore. Other phenomena, though, become the focus of a single period of instruction or a small number of periods. They might be phenomena that help students gain understanding of some aspect of a bigger phenomenon students are investigating. Yet other phenomena are everyday examples that students may have a strong experience with, but not realize that science ideas can be used to explain them. The main focus of this session is on the phenomena that take many class periods to complete. A phenomenon doesn't have to be phenomenal, but rather something people can observe. And phenomena aren't just an opening hook that gets dropped as you proceed with a unit. They really do help us focus three-dimensional instruction. Also, sometimes we have to use tools to make our phenomenon observable, because what students need is to explore is at a spatial scale too large or too small to observe directly, or processes occur over time scales that we cannot observe directly. In all cases, though, we want to try and find phenomena that are in some sense observable and focus on developing an explanation for what it is we see, even if we cannot see it all at once. As an example of something that is observable only when we look from afar and speed up time, consider this potential anchoring phenomenon for an earth science unit. What are we seeing in this animation? How are science tools magnifying this so that we might make it a phenomenon worthy of student investigation? It's valuable to think beyond Earth's surface and atmosphere too, and consider phenomena in outer space and in the deep ocean, phenomena that are on a macroscopic scale too vast for us to see without the aid of instruments and models, and on the microscopic scale too small to observe without powerful microscopes to see them. So think about what are other contrasts or type of phenomena we should keep in mind to make sure we are thinking broadly about possible phenomena. Let's now return to what defines a design challenge, something else we explored in the phenomena game. Here's the definition of design challenges. Again, what do we notice that is similar or different from what we came up with as a group for telling when something is a design challenge? What are some criteria for design challenges? Design challenges are a context where students can apply engineering design practices to create and test solutions that arise from phenomena. As noted in the definition here, phenomena are the starting places for identifying needs for which people can design solutions to problems they encounter. An understanding of the science that explains a phenomenon is central to what makes for a good design challenge. Design challenges relate directly to a big idea in the framework for K-12 science education about equity. A major goal for science education should be to provide all students with the background to systematically investigate issues related to their personal and community priorities. That is, students need to be able to see how science and engineering are relevant and can address goals and problems that matter to young people. They should be able to frame scientific questions pertinent to their interests. A core assumption is that science instruction should connect directly to students' experiences and interests and help them develop identities as people who do science and engineering, and if desired, as people who are scientists and engineers. Students should have opportunities to conduct investigations and seek out relevant scientific arguments and data, review and apply those arguments to the situation at hand, and communicate their scientific understanding and arguments to others. Promoting equity, then, means students need to have direct opportunities to engage in science and engineering practices to investigate their questions and design solutions to problems they care about. These relate also to justice aims for science education. Design challenges especially present opportunities for students to see how science and engineering practices can support goals for citizenship and community involvement, like addressing gaps in where trees are planted in the city or creating forums for youth to design and participate in democratic debates about the ethics of genetic engineering. Chapter 11 of the framework specifically addresses inclusive instructional strategies that are needed to promote equity in science education. They address 3 that can be related specifically to phenomena and how students make sense of them. For the purposes of promoting equity, it crucially describes how science learning is always a cultural process. It is important that instruction make connections with students' everyday experiences instead of emphasizing discontinuities with their everyday lives. It needs to connect to the things young people care about and to how they see themselves. These are important for equity because it is too easy to communicate the idea that other people do science, or to focus attention on aspects of experience that are remote from students' lives. We want to pick phenomena, then, that meet the criteria of being observable to the students in our classrooms. If we are not careful, we can make wrong assumptions about what those are. Another place to emphasize continuity between science and everyday lives is to ask questions about values and practices of students' families and cultural communities. In some indigenous communities, keen observation is a skill adults seek to cultivate in children. Instruction can help students build bridges between values, for example, of persistent looking over time, noticing small changes in how they relate, and particular practices to those of scientific forms of observation and ideas that one might find in an ecosystem's curriculum, for example. We can choose phenomena that explicitly bring these values and practices to bear on explanation or solutions to problems. Third, inclusive instruction begins with the premise that young people already possess ways to communicate their ideas about phenomena they encounter in their everyday lives. This is different from deficit ideas about the linguistic resources of English learners, or when students don't use scientific terminology in their explanations. Vocabulary emerges from efforts to make sense of phenomena and give a name to things that, for most of their investigations, should empower youth to use whatever means they have available to communicate their thinking, from their native language to drawing to gesture. The framework stresses the importance of inclusive instructional strategies designed to engage students with diverse interests and backgrounds, and points out that these principles should carry over into assessment design as well. We often think of building and testing physical devices as a type of design challenge, and many performance expectations call for such connections. This slide lists a few types of challenges to consider. When we think of the engineering design process broadly, and particularly recalling that it is oriented towards solving problems that address a human need, a community or societal concern, Then design challenges that engage students with learning about those needs and testing solutions that have not just technical but also social dimensions is important. An important consideration is whether there may be opportunities to link design challenges to ongoing social justice concerns and endeavors in the community. This is the end of this presentation, and thank you for listening.